Okay. Today we're gonna continue with trees. Um, and we're gonna start with what I tried to jam in at the very end on Friday, which is that trees are really similar to what we've been doing with lists, but we're gonna do a lot more with trees. In fact, we're gonna spend most of this month, I think, working on trees. Maybe even a little bit more. Um, I haven't looked at the full schedule. But in hardware, what's going to be going on with trees is this picture, right? So we have root and root. The picture here, right, shows the actual layout of tree nodes existing with a left and a right and data, which are pointers to tree nodes. And it gets a little bit messy, but that's actually what's going on in memory. When I talk about and reason about trees, what I'm going to tend to do is write the tree on the left. And in fact, as we add more and more data to trees, I'm only going to note the parts we care about in that particular discussion. So right here is the same tree on the left, but written in a much easier to visualize manner. So, okay. But there's one thing that bothers a lot of people in my experience. That if I say trees are like linked lists, and you were telling me if I had something like CSAY225X stored in a linked list, right? And I said it was a linked list, or an array, there isn't that much space used. Whereas, right, if this was a linked list, there wouldn't be that much space that was sort of extra or wasteful. But here, man, we've got all of these null pointers. All of them. Whereas in a linked list, we would have had one. So we're going to do a proof today to show how many null pointers you get in any binary tree. Okay. So our theorem is that we want to say is that if there are n data items in our representation of a binary tree, that there are how many null pointers, do you think? What's your guess? Let's go back and look at this. Let's see. We had 1, 2, 3, 4, 5, 6, 7, 8 items. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. So the n plus 1 seems to work okay. N squared. N squared would be pretty bad. 2 to the n plus 1? Ooh. N to the n factorial. Okay. We could do a big O, but we're going to do a precise count here. We're going to try, and we're going to claim that it's going to be n plus 1. At least our one example seemed to be n plus 1. So we're going to say that we want to prove the following. Let the following function nulls of n be the number of null pointers in a tree. Let's actually say binary tree with n nodes. Okay? So does this seem to work? Let's muck around with this a little bit more. Let's see. If we had a tree with one node, it has two nulls, right? Root. Now I'm going to stop bothering to draw the root most of the time. One node, it has two nulls. What about What if I draw a really weird tree? All right. So there's 1, 2, 3, 4, 5. Okay. Yes. How are we going to prove this? We're going to prove it inductively, but I wanted to do a little bit of scratching around to try and show that this seemed reasonable. And in fact, a lot of the time that's what you do, is that you will start with first working through an idea very loosely to try and get an idea, try and understand the problem, and then you try to formalize it. And that happens with code too, right? You'll come up with the way you want your program to work, and you'll describe it very loosely. But then when you have to go to code, you have to change from loose to very precise. Well, we want to prove it for all. So I agree we're going to do induction. And what's the first thing we do with induction? We need base cases. So how many null pointers are there in a tree with 0 nodes? 1. Yeah, right? A tree with 0 nodes is root. So this holds for a tree with 0 nodes. Yeah. These non-existent trees are really weird, but they actually make a lot of the things we're going to do in this class a lot cleaner as long as we always talk about these non-existent trees. So a tree with 0 nodes is, and then also we can say that n plus 1 is 1 for n equals 0. Okay. N equals 1. Well, that was pretty easy, right? Yeah, 0 nodes is an empty tree. It still has a root pointer. So our data structure with 0 nodes, that is a tree, if that data structure exists, it's using one pointer to tell you, hey, there's nothing in me. Our tree with 1 node, that's all the trees that there can be with 1 nodes, right? And then 1 plus 1 equals 2. Check. How about a tree with 2 nodes? Can we draw all the trees with 2 nodes? All the binary trees? Let's see, I think I've got this thing and that thing. That's all the binary trees, right? That have only 2 nodes. So I can still exhaustively do this. And I get 3. These checkings are easy. Okay. We're going to do one more. And we're going to do one more partially to try and think about what structure looks like. Because the next thing we're going to have to do is we're going to have to write our inductive hypothesis, and then we're going to have to actually do our induction. And to do our induction, we need to really reason about the structure of that we're working with here, right? So with nulls of 3, n equals 3, well, 3 plus 1 equals 4 is easy. But let me get that a little bit lower, okay. Let's try and draw all the trees with 3 nodes. Let's see. Here's 1. Anyone have a suggestion for another tree with 3 nodes? All left. Okay, we can have the all left tree. I like that. Okay, let's see. Okay, we got that. And we had the all right tree before, I believe, so we can draw that over here. Okay, those Then left, right, right, left, right? So we've got more. We have left, right, and right, left. Let's see, we've got 1, 2, 3, 4. 1, 2, 3, 4. Okay. So, okay, I think we've got them all now, right? All the way left, left, right, balanced, right, left, and all the way right. So this is left, 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 right, right, left, right, right, and balanced. So I think this is all the binary trees that exist with 3 nodes. And they all have 4, so our base case works. But we really didn't need this deep a base case, but it was helpful to reason about it. Is there any theorem about how many trees are possible? I'm sure there is. It's an interesting question. We'd have to inductively prove how to prove the number of different trees at every size. But here are all the trees with 3 nodes. Right? But it okay. Um so what is the same between all these trees? Not much, is there? But there is one thing, that all of these trees have a root. The number of null pointers, the number of nodes, those are true. But the structure that we want to work on is that all of these trees have a root, and then they have 2 subtrees, don't they? Because remember, we talk about empty trees. So all of these trees can be thought of as a root with 2 subtrees. And I realize some of these subtrees are funny, but all of these trees have a root with 2 subtrees. Now, could we do this in a that we are adding 1 node? This one we might be able to, but you're going to find that when dealing with a structure, that you don't want to do induction by adding to the end. That's going to often be really, really hard to show what's going on. And you're going to find that with trees and with graphs, we almost always want to take the structure and break it down into smaller structures. So if we look at this, right, we have a root with 2 subtrees in every case here. And that's a really nice, clean structure. And what can we say about those subtrees? Well, because we've removed the root, no matter what, all of those subtrees are smaller than the total tree, right? So all are smaller, i.e. less nodes than the full tree. Okay. They have 2 subtrees, but we'll note that some of the subtrees have no nodes in them, right? Right? Yes, and we can use 0, 1, or 2 for them. Okay. So let's write our inductive hypothesis now, because I think we can formulate it. We're going to want to say that suppose nulls of n equals n plus 1, for all n less than k. And again, in this case, we could think about this in a different way, but I want to show you the technique that we're going to use to prove lots and lots of properties about trees and graphs. So this particular proof is on a very simple property, so we could approach it a different way and get a clean proof. As the properties get more complicated, it is much harder to get it right. So, but do we all agree that suppose nulls of n is equal to n plus 1 for all 0 n less than k greater than or equal to 0? Okay. So now let's try to write our induction. So now we want to consider an arbitrary tree T with k nodes. So we have some tree T that has k nodes. I waited for a little bit. I would take more questions. But tree T has k nodes. Okay. So I'm going to draw tree T as this. It has a root plus 2 subtrees. Okay. Since it has k nodes, I want to express how many nodes are in each subtree. So first, let's pick a letter. Somebody give me any letter. M. Okay. M was in first, so wins. So we're going to say that there are m nodes in left subtree. Okay? And we're just choosing that. We haven't said how many. We haven't constrained m in any way. But it's a real number of nodes, so it's 0 to k minus 1, right? Okay. How many nodes are in the right subtree? K minus m, is that right? It's very close. Minus 1, yeah. Subtree. Yeah, because we have a root. Okay. So we have m in the left and k minus m minus 1 in the right. Okay. So let's now use our inductive hypothesis, and we can say that total nulls equals nulls of m plus nulls of k minus m minus 1. Does everyone agree with that? So there are a couple of tricky pieces here to make this true. First of all, we have to accept that the root has no nulls, right? Because we've already taken care of the 0 and 1 cases. And if the right subtree, for example, is empty, so, or let's do the left subtree because it's a little bit easier to word. If the left subtree is empty, if m equals 0, the null to the left of the root pointer is charged to that subtree. That's why I kind of tried to draw that these were going into the tree, because we're charging the tree for the pointer. Okay. So then we imply inductive hypothesis, and we get m plus 1, and we get k minus m minus 1 plus 1. And let's see, the m cancels the m, the plus 1 cancels that, and we get k plus 1. And we're done. So, what's important to see in this is both to refresh thinking about induction and to think about induction in this context of a data structure. Yeah, you're going to find that with a data structure, it is almost always going to be better to be doing induction by breaking it down into smaller data structures. And there's a nice thing to mirror this is that method of taking a large complicated data structure and breaking it down into smaller structures is exactly what induction does. What recursion does. Right? So this is exactly the same structure. How do I get m plus 1 and k minus m minus 1 plus 1? Well, nulls of m, right, is by inductive hypothesis. You want me to have? Our inductive hypothesis was nulls of n equals nulls or equals n plus 1 for all n less than k. Right? So we used our structure to label how many nodes there are. Okay? And we're going to find that algorithmically this technique is very useful in showing the running time of algorithms, that algorithmically this technique is very useful in figuring out how to construct algorithms that have guaranteed properties, and that proving constants of our data structures, proving that our data structures hold properties, is essentially going to be that same structure whereby doing this recursively. How many base cases did we explicitly need? You need here 0 and 1. Do we have any proofs on the exams? We will not have any full proofs, but we may have things that ask you to use techniques from the proofs or use ideas from the proofs. Would 0 be enough as a base case? The problem is with 0, let me think about this. Yeah, I guess actually 0 is enough here. And of course it should be. Yep. 0 is really all you need. I would always choose to write it as 0 and 1 because it's a little bit cleaner, but 0 correctly handles the 1 case, as you say, that R is the using the structure, not the base case. So R comes from the structure of the tree. And we would prove 1 then by 0 and 0. So m is 0 and k minus m minus 1 is also 0. Exam 1 will cover through last Friday. It will not cover this material. the practice exam is out. So, for the induction hypothesis, let's go back to here. What does n represent and what does k represents? Well, they're both just variables, right? And we have produced k is a variable that has no fixed value, but is bounding n, right? So they're both variables, and we are bounding n with k. So, right? So, instead of, if we just said this was true for everything, it would not work. But we need to say it's true for, well, at least some number of things. And the number of things is when we sort of start the base cases. But as we are proving larger and larger examples, we are saying k changes. Can we say k minus 1 has k null pointers? No. We have nothing that's... We can say that k minus 1... A tree with k minus 1 nodes has k null pointers. But how are you going to take it off? If you think about your big tree, how do you remove it? So with small trees, it's easy to imagine what you mean by removing it, right? But you have to show that I can always remove this thing. So what's happening here is I'm breaking my tree down into 3 parts. And I'm showing that these parts are always removing... that if I was trying to guarantee I remove a node, there has to be a node to remove. What node am I removing? And how do I know I get back? You really need to have a way that this description that I wrote here, this part here, right, correctly describes any tree no matter what k is, right? But to describe removing a node at the bottom somewhere or in the middle, what does removing a node in the middle mean, is unclear. It's okay. And let me be clear, that particular construction, part of why I'm stressing on this so much is that it's really tempting often to write that construction where you kind of remove a node. But here, this construction works on basically every tree proof you'll ever encounter. Of what do I do with the tree? I remove the root, and then I have 2, or in a k-ary tree, k trees. And that I can construct how things work that way. And the other thing I want to say is what we see nicely here, in a sense, is the fact that we're talking about 0 trees. So that we, in this class, talk about trees that have 0 nodes as being trees is a very clean way for this proof to work. Okay. So that's the refresher of sort of how proofs go in recursive proofs, inductive proofs, on recursive types of data structures. And you're going to see that almost everything we do from now is going to be a recursively defined data structure in some way or form, and that we are going to want to prove various properties to guarantee runtimes. And we're going to be doing this inductively all the time. Okay. So, with that out of the way, I want to start talking about how do we traverse. One of the things I described in the ADT for a tree was a traversal. And in a list, a traversal of a list is really straightforward, right? You get the first thing in the list, or the 0th thing, depending. then the first, and the second, and the third, until you get to the end of the list. You're all writing this, and hopefully most of you have written the iterator, because it's quite easy part to get done for going forwards and going backwards in MP lists. But how do you think we should traverse a tree? If I want to visit everything in the tree, how do I do that? Any suggestions? Left to right. So, like, this would be here, and then do I choose up there or down here, or check every node on a specific level? That is absolutely one. But let's do a recursive version here. We got a lot of different choices. So see, unlike a linked list, there are lots of different ways we can visit a tree. And let's choose what to me is probably the simplest. And the simplest one I'm going to say is, well, we start at the root, and we'll start by observing the first thing. And we're just going to talk about that we yell or print, and so I'm going to do it. So we're going to start by visiting the first thing. So we're going to go plus. And then I like this left, go right idea, right? So I'm now going to, traverse this tree, I'm going to visit the root, and then I'm going to traverse the left subtree, and then traverse the right subtree. So, visit root, traverse left, traverse right. Okay. There's my nice recursive function. So traverse root works as visit the root, traverse the left, traverse the right. Okay. So doing that, we've got a plus. We've visited this guy. Then we do a minus. And we recurse. And we do an A. And we recurse, and what do we do if not null? So we don't do anything if the root is not null. If the root is null. So then we recurse left, we recurse right, we recurse up, we recurse up. At minus, we recurse right. So we now visit here. Left, visit here, get B, left, right, doing nothing, recurse up, recurse down, get C, recurse down, get star, recurse down, get D, left, right, already got done, recurse up, get E, left, right, and recurse up, and we're done. Well, we did that, right? I guess not in this, so we are explicitly visiting the nulls, right? We visit the null, and then go. So the way we wrote this particular version of the recursion, we recurse into the null. So let's, if I put, say, A, E, we'll put F down here. We do E, we check there, we recurse down to F, we visit F, we check there, we check there. Right? So now we have one is not null. But it still works, right? Because traverse the root, we visit the root if it's not null, which was the plus, then traverse the left. Then visit the root, it's not null, traverse the left. So we go chunk, 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 chunk. Right? There is our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 steps of it. Is there a difference between a null and a null pointer? In C++, there is. Right now, we're just talking about a theoretical idea here. This is not an implementation. The implementation will be in C++, but, right, I mean, it's a null of some sort. It's a nothing. So, okay. So, we're going to call this a pre-order traversal. Okay. And speaking of C++, let's try and actually write this. So we want to do traversal, and we will have our pre-order traversal. We're getting passed in a tree node pointer current. Let's see, how do we write this? So, right, we are going to, for yelling, we're going to print. So, cout. Let's do cur arrows data. So that's how we visit a node. We print it, right? And which means we act on the data in some way. Okay? And then we do pre-order cur left. Pre-order cur right. Is that it? Are we all good? If not null. Okay, so let's see. How can I write that? If cur. There's our base case now. Anyone have a problem with how I wrote this? Some people like it. But what's going on? And this is a very standard way for C and C++ programmers to write something like this, but it's also a little confusing. That's right, cur might be null. Well, what do we do? If cur is null, it is 0, and 0 is false. Remember, null pointer and null is equal to 0, and 0 is false. So, I'm not arguing that this is the best way to write it. But this is a very standard way to write what you probably wanted to see, which was right? The base case It returns. You fall off the bottom of a function and you return, right? It's returning void, so I could write return a return statement that returns nothing. But when you leave the end of a function, you return to the calling function. So, right? How do we come back up? Well, here. It goes down the left, down the right, and then it hits here, right? Not cur would be 0 is false, so if cur is true, I guess, and not 0, it's just outputting it to the console. I mean, you could do other things. In a sense, right, what I really want to do is pass in some function here, and I would do some amount of work. Is not 0... Yes. So not 0 is true and 0 is false. All of this stuff happens to be true in both C and C++. It's really not a good thing that it's true, but it is a fact that people depend on in writing a lot of code. Right. So if cur and if cur not equals null pointer are exactly the same statement, assuming cur is a pointer. And again, I pointed out the if cur formulation because many long-term programmers will write it that way. Would the code inside if not cur only run if cur was null? Yes, I believe so, but I've never seen people write it that way. That is to say, if you want it in the case when it is null, I see people do it the other way. Yeah, the else does nothing. This whole piece is completely optional. I just thought it was showing it so it was a little bit clearer for people that were confused about what was happening, that were asking what the base case was. And the base case existed even if I didn't write else, and the base case is do nothing. I'm at a null. And if I was writing it, I would not have written the else. If cur. So the trick is that if treats any numeric result as a Boolean and evaluates it that if the value is 0, it is false, and if the value is true, it is if the value is not 0, it is true. It recurses up here. So if I'm at the base, I do nothing, and I return here when I fall off the end of the function. So I return either here or here, right? when I end this function, so I call this function, which calls this function, which calls this function, which calls this function, which calls this function. Well, I return to where I was. If I was on the left, I return here and then execute the right. If I was on the right, I go out and return again. The complexity and the runtime are the same for the recursive versus iterative here. There is a slight space complexity that exists in the recursive form that could be gotten rid of in an iterative version. It's not really important in most cases with a tree. And tree code is so much easier to write recursively. That's what we're going to expect you to do. So we will not be penalizing you for recursive versions of tree calls. Traversals will not be on this current exam. So what is the complexity of this? So that's a good question. What is the total complexity of this? Now, I could force you to do a fully inductive proof that, right, this is going to have a complexity of 1 plus the complexity of the left recursion and the right recursion. But I'm going to short circuit and say it's going to have a complexity of n. So it's big O of n. Right? And it's big O of n because as I do this recursion, I will call this line, this cout, once on every single node, and not more than once, right? I never return to a node. I return to the code at a node, but not to the node itself. It's also the minimum. In this case, the complexity is hard. It's also big omega. So we have a strict upper and lower bound. The running time is exactly linear. So the most time it'll take is n, and the minimum time it'll take is n. Can we pass a function on nodes to this traversal to do operations on each node? Not as I wrote it, but absolutely you could use a function pointer or use a functor and have that operation happen on each node. Absolutely. But in C++, what we're more likely to do is to write a functors in C++ are not the same thing as they are in Haskell. They're ugly and kludgy, and we don't really do them. But they do exist. Haskell functors are much nicer. C++ functors are, you can create a class that overloads the parenthesis operator, and that's a function, so, yeah. Functors are similar to lambdas, and lambdas, while their syntax in C++ is ugly, are much closer to what you get with functors in Haskell. But I'm letting myself get off the track. This is all I'm doing for today. I'll answer questions more as we go, but that's it. I'll stick around and take questions, but that's it for today.